Hey everyone, and welcome. Today, we're going to tackle one of the most powerful ideas in all of digital signal processing, discrete time Fourier analysis. We're about to see how just changing your point of view can unlock a whole new way of understanding the signals all around us.
All right, let's kick things off with a question. You and I, we can instantly tell the difference between a flute and a trumpet, right? Even if they're playing the exact same note. But how does a computer do it? How does a machine that only understands numbers figure that out?
And the answer? It's actually pretty elegant. The computer does it by seeing the sound's unique recipe of frequencies. See, even though the main note, the fundamental frequency, is the same, all those other subtle, higher frequencies, what we call overtones, are totally different. That unique mix is the instrument's sonic signature. And that right there, that leads us to the absolute core idea for today. There are two fundamental ways to look at any digital signal, and you really need to get both to unlock its secrets. So first up, we've got the time domain. This is the way we naturally think about things. It's a graph showing how strong a signal is, its amplitude, as time goes on. You can think of it like a series of snapshots, one after another, telling the story of the signal from moment to moment. Okay, now check this out. This is the exact same signal, I'm not kidding, but we're looking at it in the frequency domain. Instead of plotting strength over time, this view shows us the strength of each pure frequency that's mixed together to create our signal. It's the ingredient list, the recipe we were just talking about. Which, of course, begs the question, how do we do that? How do we jump from that familiar world of time into this powerful new world of frequencies? Well, we need a portal, a mathematical portal that lets us translate between these two languages. And that amazing tool is called the discrete time Fourier transform, or just the DTFT for short. Now, formally, the DTFT is the math that takes our sequence of samples from the time domain, our x of n, and turns it into this continuous function of frequency. I know that equation looks a little intense, but seriously, don't sweat the formula itself. The important thing is to just get what it does. And honestly, the absolute best way to think about it is like a prism. You know how a prism takes a single beam of white light, which just looks like one thing to us, and splits it into all its different colors, into a rainbow? The DTFT does the exact same thing for a complex digital signal. It breaks it down into a spectrum of simple, pure frequencies. So the whole journey is really just a simple three-step process. You start with your signal in the time domain. You send it through that DTFT portal, and boom, you arrive at your destination, the frequency spectrum, a complete map of everything that makes up that signal. Okay, so we've made the trip, we're in the frequency domain, now what? What does this new map actually tell us? What can we learn from this perspective? This spectrum, it tells you so much. Where you see a peak, that tells you exactly which frequency is in the signal. And how high that peak is, that tells you how strong it is. This is the signal's unique fingerprint. So for a trumpet, you'd see a big peak for the main note, and then a very specific pattern of smaller peaks for its overtones, a pattern that would look totally different from the flute's fingerprint. Now, here's something kind of weird, but super important. Because our signal was made of discrete samples in time, its frequency spectrum is periodic. It literally just repeats itself over and over again. This means all the unique info we need is packed into one single chunk. And this is a direct result of sampling a signal in the first place. It's actually why we have to sample fast enough to make sure these repeating copies don't overlap and mess each other up. All right, so this frequency perspective isn't just for looking at signals, it's also the secret to modifying them. And that brings us to this idea of a system's frequency response. So in signal processing, a system is just a fancy word for anything that changes a signal. Think about the audio equalizer on your music app. That's a system. It's a filter. And the frequency domain is the absolute perfect place to understand what that filter is actually doing to your music. So, just like a signal has a fingerprint, a system has one too. We call it its frequency response. You can think of it as a guide or a set of instructions that tells you exactly how that system is going to treat every single frequency that tries to pass through it. Is it going to boost the bass, cut the treble? The frequency response has all the answers. And you can see it in action right here. On the left, we've got the spectrum of our input signal. See that mix of low and high frequencies? Now look at the right. After we've passed it through a low-pass filter, you can see clear as day. The high frequencies have been totally squashed. The filter let the low ones pass right through. And here it is. This is the mic drop moment, the whole reason this is such a game changer. That complicated filtering process, which in the time domain involves a really messy calculation called convolution, becomes simple multiplication in the frequency domain. You just multiply the signal spectrum by the filter's frequency response. That's it. This one trick is what makes so much of modern digital signal processing even possible.
So, let's bring it all home. Why do we even bother with all this? Why take this journey to a whole other domain? Well, because this change in perspective, it's like gaining a superpower.
We use it everywhere. It's how engineers design the audio equalizers in your car. It's at the heart of how Siri and Alexa understand what you're saying. It's the magic behind MP3s, which cleverly throw away the frequencies our ears can't hear to make files smaller. It's even the theory that proves we can turn a digital signal back into a perfect analog sound wave. At the end of the day, by making that trip from the time domain to the frequency domain, we gain the incredible power to see the hidden recipe inside every signal. And that lets us analyze, change, and build the digital world around us with amazing precision. So the next time you listen to music on your phone or use a voice command, think about that hidden world. Think about the journey those signals took and ask yourself, what hidden frequencies are being shaped and molded right now to make it all possible? Thanks for joining me.